Hello, calculus students. Today we are going to take a deep dive into advanced integration by parts. And the reason I call this advanced integration by parts is just because we're going to go beyond what's typically taught in like a BC Calc class and do a little bit more. So stick with me and let's get to it. So integration by parts is really a technique of integration that comes from the product rule. And the integration by parts technique has a formula, and it says the integral of u dv equals u times v minus the integral of v du. So what that means is you start with this integral on the left, which is the integral of a product, and then on the right, the answer to that integral, the antiderivative, half of the antiderivative is done for you, and then hopefully you can do the other half by yourself. And I said it comes from the product rule, so let me kind of show that to you. If you took d dx of u times v, where u and v are functions of x, the product rule says that's going to be the first times the derivative of the second, plus the second times the derivative of the first. Well, one of the things about equations is that as long as you do the same thing to the left and the right, you're just fine. So what I could do is if I really wanted to, I could integrate the left and integrate the right. Well, the integral of the derivative, those are opposite operations, so those effectively, come on, OneNote, those effectively cancel out. So I still have u times v here. And on the other side, I'm going to distribute that integral across the addition. And then with some magic called subtraction, I can subtract v du from both sides, and I get u times v minus the integral of v du equals the integral of u dv. And that's the integration by parts formula. Okay, so again, the integration by parts formula says, in a sense, if you want to integrate a product that you don't know how to integrate, you call one part of the product u, the rest of the product dv, and then calculate u dv, v du, all of those, and throw them into this formula to get your antiderivative. Okay, so that's the backstory. Now let's actually do it. How do you pick? I've got the integral of u dv. How do I pick which part's u and which part's a dv? Well, that's a big question, but one thing you can do to help you get started is if you're not sure which part of the product is u and which other part of the product is dv, you can remember LIATE. LIATE. If you sing it like a monk, sometimes it makes it easier. So LIATE stands for logarithms, inverse trig, algebraic, trig, and exponential. You look at your expression, you look at your integrand, and see if you have any logs. If you do, that's your u. If you don't have any logs, do you have inverse trig? If yes, that's your u. And you just go down the line to help you pick u. So let me show you what I mean. What if I had the integral of x e to the x dx? LIATE. Okay, do I have a log there? Nope. Do I have an inverse trig? Nope. Do I have an algebraic? Yes. Yes, I do. Algebraic stands for x raised to a numerical power. And that's what I have. I have x to the first here. Okay? So I look at the integral of x to the x and I think, do I know that antiderivative? No. No, I do not. Is a u sub going to help me? Nope. Not going to help me there. So let's try integration by parts. U is going to be x, which means dv is everything else, e to the x dx. To use the integration by parts formula, I also need du and v. So now I'm going to calculate those. The derivative of x is 1 dx. The antiderivative of e to the x is e to the x. So the integral of u dv, which should be my original, and it is, equals u times v minus the integral of v du. They took half of the antiderivative for me using the formula, thank you, and then I have to do the second half of the antiderivative by integrating e to the x, and I can integrate e to the x myself. X e to the x minus e to the x plus c. So we just found out that the antiderivative of x e to the x dx is itself minus e to the x, maybe plus a constant. And there it is. So one way to use integration by parts is to have a product that you can't just get rid of, and then you separate that product into u and dv and go from there. Well, if I look at number 2, I don't have a product. I just have the integral of ln x dx. But here's the thing, ln x dx is a product. There's ln x and there's dx. And if I look at the integral of ln x dx, I think, do I know the antiderivative of ln x? Gosh, I don't think I do. I don't think that's one of the ones I had you memorize. Now, I do know the antiderivative of ln x. I'm just pretending. So let's pretend I didn't know the antiderivative of ln x. I can let integration by parts do it for me. And I can say, well, I don't know the antiderivative of ln x, but I do know the derivative of ln x. So LIATE, do I have any logs? Yes, I do. ln x is a log. So I'm going to say u equals ln x, and then dv is everything else, which is just dx. And if I want to remember, dx is really like 1 dx. And then I'll calculate du into v. Well, the derivative of ln x, we know that one. That's 1 over x. And the antiderivative of 1 would be x. So the integral of u dv equals u times v minus the integral of v du. So there's half my antiderivative in the front. And now I need to integrate myself x times 1 over x. Well, x times 1 over x is just 1, and the antiderivative of 1 is x. So x ln x minus x plus c. So we just learned that the antiderivative of ln x is x ln x minus x. And that's something, honestly, that is good to commit to memory. The antiderivative of ln x is x ln x minus x plus a constant. So if you can, shove that in your memory banks somewhere. What's the antiderivative of inverse tan? I got to be honest, I don't know this one. Okay, I know how to get it, but I've never taken the time to memorize it because honestly, it's a pain in the neck to memorize, so I don't. But what I do remember is that I can take the antiderivative of inverse tan using integration by parts. So that's what we're going to do right now. LIATE, logs, nope, inverse trig. Yeah, that's what I got. So u is going to be inverse tan x, and dv is going to be everything else. So the derivative of inverse tan, yes, you need to know it, is 1 over 1 plus x squared, or du over 1 plus u squared. All right. And the antiderivative of dx would just be x. And so if I want to do integration by parts with this, I have the integral of u dv equals u times v minus the integral of v du. And then I realize, oh, that second integral, it's pretty big. X over 1 plus x squared. Well, how can I take the antiderivative of that? Well, I have a quotient, and I got an x on the top and an x on the bottom. So let's try a u sub here. U could be the denominator, 1 plus x squared, which would make du 2x dx. And I don't need 2x dx, I just need 1x, so I can multiply both sides by a half. Okay, I'm feeling pretty good about this. So this becomes minus the integral of, let's see, 1 over u times 1/2 du, which would become minus 1/2 ln absolute value of u plus c. And so then with that, I've learned that the antiderivative of inverse tan x is x times inverse tan x minus 1/2 ln 1 plus x squared plus c. And now you know why I've never committed that to memory. Because it's weird. Life isn't fair, and integrals don't make sense. Again, integrals do make sense, but they're not always predictable. And there it is. And if you're thinking, but Mrs. Vibber, where'd that absolute value go? I don't need it. 1 plus x squared is always positives for every value of x, so that absolute value would be redundant. So I just use parentheses instead. Ta-da! What next? Let's try a chart. What's a chart? All right. So sometimes when you do integration by parts, you have to do it over and over and over again, and it gets really tedious. It works, but it gets really tedious. So before we try this chart, I just want to show you what would happen with this one if I did integration by parts. And if you want to skip writing this down, go right ahead. This is one of those times where I'm going to show you how annoying it is to show you why we have another method of doing integration by parts. All right, so there's a product, x squared sine x. I don't know the antiderivative of x squared sine x, so I say, all right, well, LIATE, no logs, no inverse trig, algebraic, I got that. So u is going to be x squared. Du is going to be 2x dx. dv is going to be sine x dx, making v negative cosine x. So the integral of x squared sine x, u times dv, equals u times v minus the integral of v du. So I'm actually going to make that plus 2x cosine x dx. 2x cosine x dx requires another integration by parts. LIATE, so u would be 2x, dv would be cosine x, then v would be sine x, and du would be 2. So then this would be negative x squared cosine x is still there, plus u times v minus the integral of v du, whose antiderivative is then, get the front stuff in there, antiderivative of 2 sine x would be negative 2 cosine x, with this other negative would become positive 2 cosine x plus c. Whew! I needed a double integration by parts. It works. I got an answer. But if that were x cubed, I'd need a triple integration by parts. And all kinds of other things could happen where your integration by parts just keeps rolling down the hill, and sometimes it takes a while to get to the bottom. So there is a chart. Now, I got to be honest, I'm not a huge fan of the chart because there's really no saying what you're doing as you're going through it, but it works and it shows you the derivatives and the antiderivatives that you would need. All right. So here is how the chart works. And if you haven't been writing, pick up your pencil and write now. You are going to make a chart that says plus minus u dv and product. Okay? In the first row, you are going to skip the plus or minus, you are going to skip the u, and you are just going to write dv. So just like you would when you start, you would say, all right, LIATE, what would be u, what would be dv? Well, u would be x squared, dv would be sine x. So sine x is going to go right here in dv. That's row number 1. Then, starting in row number 2, okay, starting in row number 2, you're going to go plus, minus, and just go down a bit because you don't know how far you're going to need to go. Let's see, dv was sine x, so then that makes u x squared. Okay, and now here's how the chart works. As we work down this column, we take derivatives as we go down. As we work down this column, we do antiderivatives. Okay? So in this column, the derivatives of x squared would be 2x, 2, and 0. And then I can stop. Once I get to 0, you stop. In the antiderivative column, the antiderivative of sine x would be negative cosine x. The antiderivative of negative cosine x would be negative sine x. And the antiderivative of negative sine x would be cosine x. And the antiderivative of cosine x would be sine x. Then I put the product on the right. A positive x squared times negative cosine x is going to be negative x squared cosine x. A negative 2x times negative sine x is going to be a positive 2x sine x. A positive 2 times cosine is going to be a positive 2 cosine x. And a negative 0 times sine x is going to be 0. So what does that tell me? That tells me that the integral of x squared sine x dx is equal to the sum of all the stuff on the right. Negative x squared cosine x plus 2x sine x plus 2 cosine x plus c. And if we compare, you will see that this thing and that thing are the same. Okay? Okay. So that is looking pretty good. And you know what I want to do? I want to do another chart. As I'm saying this, I know that you have something in front of you that says be creative with sine cubed, but I actually want you to cross that off and give us a little bit of time here with another chart. So let's do, for example, the integral of 4x to the fifth e to the 2x dx. Let's say I wanted to take that antiderivative. All right, 4x to the fifth e to the 2x. You know what? Even if I try to use sum, it's not going to help me. So we are going to do integration by parts, but we're going to use a chart. All right, so 4x to the fifth e to the 2x. So let's build the chart. I'm sorry for my jumpy screen. Plus minus u dv and product. And let me write out some of my rows here. Skip the first row, plus minus, plus minus. See if I need to keep going. Liate. Well, I have an algebraic. 4x to the fifth is going to be u. Again, skip a row. And then dv goes above it. So that's going to be e to the 2x. All right, now I'm going to take derivatives in the u column. 4x to the fifth, 20x to the fourth, 80x to the third, 240x squared. Okay, I got to keep going here. 480x, 480, 0. Okay, so I need to do that on the other side. So e to the 2x, the antiderivative of e to the 2x is 1/2 e to the 2x. Antiderivative of that would be 1/4 e to the 2x. 1/8 e to the 2x. 1/16 e to the 2x. 1/32 e to the 2x. 1/64 e to the 2x. And 1/128 e to the 2x. And honestly, that last one I don't need because it's going to get multiplied by 0, but I just felt like writing it. Okay, now I do my product. Again, skip the first row. So 1/2 times that is 2x to the fifth e to the 2x. And then negative 5x to the fourth e to the 2x. And then positive 10x cubed e to the 2x. And then negative, let's see, what's 240 divided by 16? That's going to be 15x squared e to the 2x. 480 divided by 32 is another 15x e to the 2x. 480 divided by 64 is 7.5. Let's see, e to the 2x and 0. So the antiderivative of 4x to the fifth e to the 2x is going to be the sum of all of this nonsense. So this antiderivative is equal to all of that. Okay. One other reason that I wanted to do this chart is, let's say you wanted another antiderivative. Let's say you wanted the antiderivative of 240x squared times 1/8 e to the 2x. The antiderivative of that would be all of this stuff. And so what we end up doing is, later on, when we do some integration by tables, which are really like preformed formulas, some of those preformed formulas come from these patterns that we see in these charts. So I wanted you to see another example of the chart so we could do that. Hooray! All right, I have been talking for a long time, so if you need to pause and take a break, please feel free. I am going to keep going because we've got just 2 more examples left. But if you need a break, take a break. All right, 2 more. Integral of e to the x sine x. this one's a fun one. This is one of my favorite applications of integration by parts because it's just, I don't know. I like it when fun things happen that you didn't expect and you go, oh, you can do that? Yeah, you can do that. So let's see what happens. All right, so I have e to the x times sine x. What's the antiderivative of e to the sine x? E to the x sine x. I don't know. That's a product. Let's use integration by parts. Okay. So integration by parts, LIATE. So it seems like my trig should be my u sub. Fun fact, you can also do this by letting e to the x be your u sub. All right. Maybe if I have time, I'll do that too. All right, so LIATE. So sine of x is going to be u, and then dv is going to be e to the x dx. Now, I got to be honest, we could technically use a chart for this, but we'd end up back at integration by parts anyway, so the chart isn't all that helpful. So if you're wondering, wait, you just taught me the chart, now I'm not using the chart? Yeah, that's true. The chart is usually helpful when you're using an A as your u sub. When you're using an algebraic as your u sub, then the chart is often very helpful. But anyways, LIATE, sine of x is going to be u. E to the x is going to be dv. So du is cosine x. E to the x is v. So the integral of e to the x sine x dx equals u times v, minus the integral of v du. Okay, so now I have e to the x cosine x. That feels like I need another integration by parts, and I do. So u is going to be e to the x. No, u is going to be cosine x, LIATE, cosine x. And then dv is going to be e to the x. And the derivative of cosine is negative sine x. So now I have the integral of e to the x sine x dx is going to be e to the x sine x, which I already had, minus another integration by parts formula. U times v minus the integral of v du. And then if I distribute that minus, it's minus e to the x cosine x minus the integral of e to the x sine x dx. Okay, now I've got e to the x sine x. I need another integration by parts, but hold on a minute. I already did that. I'm back to the beginning, which is why I called this one running in circles. Oh my God, I just did integration by parts. I ended up back where I started. What do I do now? It's just going to keep happening. Here's the cool thing about equations. When you have equations, as long as you do the same thing to both sides, it's fine. And you know what I realized? I have like terms. There's an integral of e to the x sine x. Here's an integral of e to the x sine x. Maybe they should meet up somewhere. Yeah, they should. So what we're going to do here is I'm going to add the integral of e to the x sine x dx to both sides. You can do that? Yes, you can. So now what's going to happen is I have on the left-hand side 2 times the integral of e to the x sine x dx. And on the right-hand side, I have e to the x sine x. I'm running out of room, so you know what? Let me move this. So on the left, I have 2 times the integral of e to the x sine x dx. And on the right, I have e to the x sine x minus e to the x cosine x. Okay? And then I can just divide both sides by 2. So the integral of e to the x sine x dx is 1/2 e to the x times sine x minus cosine x plus c. And if you're thinking, Mrs. Fibber, where did that c come from? It's because I've kind of been waiting for a plus c until the end. It's kind of always existed in there, but we just don't write it out until the end. So I'm building in a plus c that kind of disappeared because when I did this step, I didn't actually evaluate that integral and create the plus c that I wanted. So when you have some kind of cyclic integration by parts going on, once you get an integral that you already had on the left, you can combine like terms, and that's cool. All right, one more to go. Example 7, which I like to call black magic just because it's really fun and funky, is going to have some interesting things that happen. So I have the integral of secant cubed x dx. Doesn't really feel like a product. So I have a couple options here. Option 1, u equals secant cubed, and then dv equals 1 dx. I'm going to tell you right now that is not very helpful. So what we're going to do here is I'm going to rewrite secant cubed as secant squared x times secant x dx. Why? Well, number one, because secant squared has some Pythagorean identities that go with it that may or may not be helpful. Narrator voice, they're not. Also, because secant squared is something whose antiderivative I actually know. So when I go to say LIATE, all I have are t's. So LIATE really exists or evolved from the idea that you want to choose something for u whose derivative you know, and you want to choose something for dv whose antiderivative you know. So when I go to do LIATE here, dv is going to be not sine, secant, pardon me, squared dx. And u is going to be secant x, because in the world of derivatives and antiderivatives, I know that the antiderivative of secant squared is tangent, and I know that the derivative of secant is secant tangent. Okay? Had I reversed those, the derivative of secant squared would be a big long chain rule, and the antiderivative of secant, yeah, I don't even know that. Okay, I do. I'm lying. But let's pretend for a second you don't know that right now. So if I want to integrate secant cubed, I'm going to change it to secant squared times secant. I'm going to let secant squared be dv. I'm going to let secant be u, and then I'm going to go from there. So the integral of, let's see, u dv equals u times v minus the integral of v du. Okay, LIAT. All right, so I've got that. Wow, that second integral looks pretty big, so let's kind of roll with it. So I have secant cubed over here, and over here I have secant x tangent x minus the integral of tangent squared x times secant x dx. Wow. What do I do with that? Well, maybe I could try integration by parts again to see what works, but I'm actually not going to do that. You could get there doing integration by parts again, but it would be in a different way than I'm about to do. Remember I mentioned that like secant squared is nice because there's Pythagorean identities that go with it? Tangent squared has a Pythagorean identity too. And if you're thinking, what were those Pythagorean identities again? Those were the one that said sine squared x plus cosine squared x equals 1. So if I divide both sides by sine squared, I would get 1 plus cotan squared equals cosecant squared. And if I divided both sides by cosine squared, I would have tan squared plus 1 equals secant squared. So what I can do is I can come down here and say, you know what? I'm going to rewrite this as tangent squared is going to become secant squared x minus 1 times secant x dx. And I'm going to use that and say, well, how does that help me? Well, how that helps me is I can distribute this and say now I have secant x tangent x minus the integral of secant cubed x minus secant x dx. And then realize, wait, secant cubed is something I've already dealt with, so I'm going to use a property of integration to say that when you're integrating a difference, this could be the integral of secant cubed x dx plus the integral of secant x dx. Okay, basically this integral can apply to both of these. And then that negative would distribute. And then I can come back over and realize, wait, now I can combine like terms, add this secant cubed x dx to the other side, get 2 times the integral of secant cubed x dx equals secant x tan x plus the integral of secant x dx. Okay, that's looking pretty good. So now I just need to integrate secant. What's the antiderivative of secant? Yep, still don't know. Here's why I call this one black magic. Is number one, we're doing a whole bunch of switcheroos. But here's the black magic part. A long time ago, somebody with more insight than I did said, God, I don't know what the antiderivative of secant is. I know what the antiderivative of secant squared is. I know what the antiderivative of secant tangent is. So if only that secant were a secant squared or a secant tangent. I know, just for fun, let's take that secant, put it over 1, and multiply the top and the bottom by secant plus tangent, just because I can. Really just multiplying by 1, right? So then that would become the integral of secant squared x plus secant x tangent x over secant x plus tangent x. Okay, well, I know the antiderivative of the top. Oh. What's the derivative of secant? Secant tangent. What's the derivative of tangent? Secant squared. What we really have here is we have a u sub. This is u. This is du. So this is really the integral of the derivative over the original. The integral of du over u is ln u. So this antiderivative is ln secant plus tangent. In order to take the antiderivative of secant, you multiply by secant plus tangent over secant plus tangent, which gets you a du over u scenario, which means that the antiderivative of secant is ln secant plus tangent. And then, last but not least, I still got to divide by 2. So we just found out after all of that nonsense that the antiderivative of secant cubed is 1/2 of secant x tangent x plus ln secant x plus tangent x. I think I might have said plus a moment ago when I didn't really mean plus. Plus c. Holy moly. Look at that. Oh, I got to zoom out even more. That was fun. Okay, now, because I'm still talking and I just want to keep talking, we did the antiderivative of a bunch of different secants all in one problem, and that's kind of cool. And you're thinking, no, Mrs. Bimmer, no, it is not cool. We just found out that the antiderivative of secant cubed is 1/2 secant tangent plus ln secant plus tangent. We also know that the antiderivative of secant squared is just tangent, and we found out that the antiderivative of secant to the first is ln secant plus tangent. All of those just differed by a power in the first place. I gotta write it out. Oh my god, I need to calm down. I haven't even had caffeine yet today, guys. My teacup, it is empty. No caffeine yet, and I'm still like this. We just, in that problem, learned that the antiderivative of secant is ln secant x plus tangent x, obviously, plus c. We also noticed that the antiderivative of secant squared is just lonely little tangent. And the antiderivative of secant cubed is, what was it? It was 1/2 secant times tangent plus ln secant plus tangent. Whoa! That's cool. Okay, I'm going to stop now because I'm getting a little overexcited. Hopefully, you've realized you've learned something and you don't hate me. Everybody have a glorious day. I hope this video works because it took a long time to make. See you later.